Okay, so in this video, we're going to be talking a bit more about direct proofs a little bit more. So in the previous video, we introduced theorems, propositions, proofs, etc. Right? And we spoke a bit about some definitions involving even and odd integers. And in this video, we're going to be talking about a little bit expanding on that about rational numbers. Right? So this is 4.2. In 4.3, we'll talk about divisibility. And in 4.4, we'll talk a little bit more about the quotient remainder theorem. All of these are direct proofs. And then we'll end off the chapter by speaking about some indirect proofs. Okay? So let's get started. So here we are to our first definition in this section, which is that a real number R, right, is rational if and only if it can be expressed as a quotient of two integers with a non-zero, so this is very important here, non-zero denominator. A real number that is not rational is obviously irrational. So we have to formally state this now. So more formally, if R is a real number, then R is rational if and only if there exists integers, some integers, say A and B, such that R is equal to this fraction here. The form of this is very important because we will need, when we have to tackle some proofs in this section, we will need this sort of construction of how a rational number looks in order to begin our proofs. Okay, so let me just pull up my notebook here. Okay, so let's just remember what we had from the last day, which is direct proofs. Okay, so direct proofs. Let's just remember what we had before we move forward. So if we want to utilize the theory that we have learned from the beginning of the course, which is all the syllogisms, etc., right? We can use the statement P implies, okay, use double implies, Q, right? So this here is of the form of a direct proof, right? Just using the understanding that we previously had from the first section. So because I know that this section is something new and it may be strange to us. So by using what we have previously learned, that is the notation, maybe it might appeal to our better sense. Okay, and maybe it might be a little bit easier to understand this section. So this is the form of a direct proof, right? And then from this direct proof, we have some steps that we do, and then we use, of course, like we said before, we use axioms, we use definitions, etc. And then we prove some stuff, right? And then we proved, like, I can't remember, we proved like for even, every even integers is even, and so on, right? So now that we remember that, let's go back to our slide here. Okay, so the methodology from the previous section is just extended here a bit, but instead of even and odd integers, etc., we use, we're speaking about rational and irrational. Yeah, right. So here are some examples of rational numbers and irrational numbers. So 2 divided by 0 here, that is a rational number. Sorry, 10 divided by 3, right? So A. 10 divided by 3, is it a rational number? Yes, it is a rational number because it can be written in the form, right, of this P upon Q or A upon B or whatever that you use, right? What about this one here? Negative 5 upon 39. Yes, it is. So it's also a rational number. A decimal as well is also a rational number. It can be written in the form of this fraction here, right? We had this one here with, which I was looking at first, 2 divided by 0. That is not a number. right? Because division by 0 is not allowed. So this property here is very important for us moving forward. And we have some more examples here, which brings us to this important property here, which we will need, okay? Especially in our tutorial sheets and our assignment number 2, etc. The zero property, the zero product property to be more formal. If neither of two real numbers is 0, then their product is also not 0. So we can use this zero product property in our proofs, and it will make simplification much easier for us, right? So put a star by this one. This is very important for us in this part of the entire course, right? It follows that m plus n divided by mn is a quotient of two integers with a non-zero denominator and hence is a rational number. This property will become very important for us moving forward. So we're going to generalize here. This is as well for your self-reading, as well as this example. We know all this already, right? It just expands on what we have previously spoken about, as well as this. But we reach this theorem. So the theorems I really want to focus on, and the results and the definitions, because we need those in order to prove our questions, right? This one says every integer, is a rational number, right? So we can formally prove this directly or indirectly, but we will stick to proving these things directly. Proving properties of rational numbers. So just like in the previous section where we had a bunch of different theorems and definitions and results, where we had a bunch of even and odd integers, and then we can generalize all these theorems and get a bunch of results which we can then use at some point in time if we have to prove something else. The same thing applies in this section. So we will have a bunch of different theorems with rational numbers, and then we could gather all of them. Of course, we will have to do the proof of a lot of them and remember the proofs, of course, and then we can use those new theorems to prove some other difficult ones. So the next example shows how to use the method of generalizing from the generic particular to prove a property of rational numbers. So this here. So prove that the sum of any two rational numbers is rational. So after a while, when we continue to do proofs like this and proofs in the next section 4.3 and moving forward, you're going to realize that there's a certain pattern to proving these sorts of theorems, right? Once we are able to recognize the pattern, and then from the moment that we see one of these theorems, we can immediately start to mentally see how we are going to approach these sorts of proofs, what we need to begin, how we need to begin, what we need in somewhere in the middle, and sometimes what the conclusion is, right? Or at least one of these things. If we can see the conclusion of what we need to get to, right, then we could just work backwards. So we have here, begin by mentally or explicitly rewriting the statement to be proved in the form of for all something, right? So it says prove the sum of any two rational numbers. So it only gives us two. Remember what we said at the beginning, an example is not a proof, right? So we can't give an example here and then say hence get two fractions and add them and say, well, look, the sum of any two rational numbers and I get a rational number. Then that means I will have to do it for all rational numbers, and we don't have the time to sit and write an infinite number of the sum of two rational numbers, which is why we need generalization here. So the formal restatement is for all real numbers, R and S. So we just choose random letters here. If R and S are rational, then the sum of them is also rational. So these are some questions here you have to ask yourself. Where am I starting from, or what am I supposing? And we can add another one here, like what is my conclusion? How do I get there? So when we ask ourselves these questions, then we are able to understand how to begin these proofs. So we want to show R plus S is rational. That is what we want to show. So how do I get from the starting point? Now this is where the definitions and the theorems that we previously learned, right, becomes very important. Because if we know some interesting results, then we can just use them here, right? So we know the form of a rational number here. So R is equal to A upon B and S is equal to some C upon D. We must say that B is non-zero and D is non-zero. Well, this wouldn't be a rational number. So if we add these now, generally speaking, then we get this. So we can apply the normal rules here of adding fractions, get a common denominator, and then we get this form here. So once we get that now, is this fraction a ratio of integers? And the answer to this is yes, because products and sums of integers are integers. So therefore this and this are both integers. Is the denominator non-zero? Yes. Why? By the zero product property, which is why I said that that piece of information in slide 9, I believe it was, this here, is very, very, very important. It will come back in almost all of the proofs in this section. Almost all. Right? Okay. Yeah, by the zero product property, and thus R plus S is a rational number. So that is how I would lay out my proof, so to speak, right? Now, this one asks me to prove that the sum of any two rational numbers is a rational number. I have proved it here, so therefore I get this here. The sum of any two rational numbers is rational. And then we can go to the product and then the difference and etc. like that, right? So by doing more proofs like this, and you can read this one, right? By doing more proofs like these, we get a bunch of results. So deriving new mathematics from old. So when we ask to prove something directly from definitions, and sometimes the question may ask, prove directly from using only definitions that whatever it is asked to be proven, right? Will mean that you should restrict yourself to this approach, right? So learning the definitions is important even if we are not asked to prove directly from definitions. In any case, we need to know them because we need to use them. Okay. However, once a collection of statements has been proved directly from the definitions, another method of proof becomes possible. So by doing these, playing around with these rational numbers, we get all these results here. Starting with number 1, the sum, product, and difference of any two even integers are even. We could do the same thing for the odd, the product of even integers. We could do it for the sum. So we have all these here, and all of these can be proven directly or indirectly, but we'll stick to direct proofs, right, in this section. So this is an example for your reading. And this slide 30 here gives what is a corollary. But remember, we have already defined what a corollary proposition theorem is in the very first lecture, right, at the beginning somewhere. Of course, we also spoke about what is a conjecture, right? So this here is an example of a corollary. The double of a rational number is rational. The methodology that we use for this is the same as the proofs before. And this is the beginning of the proof here. So in most of these, you see that we begin by using a formal restatement, right? So you do not need, in most cases, to do a formal restatement. The formal restatement here is just because we are now proving the theorem, but you will be using these results, right? So when you are using these results, you don't need to go and restate it in another way to make your proof easier. I mean, of course, if what is asked to be proven can be restated in order to make your proof easier, that is also fine as well. Okay. So we are sticking to direct proofs. However, We can prove indirectly, right? But let's go back here to my board. Get my pen. Okay, great. Suppose now we are asked to prove something. Let's do an example. Let's say, let's do example. Right, so suppose in this example now, I am asked to prove for all, let's give it restatement immediately. Prove that for all, so prove that for all x inside a set of real numbers, if x squared is, let's have the bigger one, irrational, but since we are dealing with rational and irrational in this section, if x squared is irrational, then x is irrational. Right? Now here's the problem with this. Not so much as a problem, but we know what a rational number is. Right? We know the form of a rational number. Now, we know that if, from our definition, back here, let me pull it up. From the very beginning, we had that here. A real number that is not rational is irrational. But all our proofs start with this here, r is equal to a upon b. So now, how do we prove that something is irrational here, but we have to use a direct proof? So how would we do something like this? So let's write proof, right? In a direct proof, right, we assume only that x squared here is irrational, but that is far too little information for me to get started, right? So the only method here that I can use to prove this is by something called the contrapositive, and we have met that before, right, in the last section. So since I know what a rational number is, I can use the contrapositive and maybe prove from that. So I can say, let's start by saying let right, so let x be an arbitrary real number. Want to prove, so you can put proof by contrapositive. Okay. So if we are proving by contrapositive, we are given if x is not, so we have if x is not, right? Remember contrapositive, we put a not in front, irrational, then x squared is not irrational, right? So that is the same thing. So that is the same thing. So we could say this is the same as writing if x is rational, then x squared is rational. Now, this is what we're going to try to prove now, because we know the form of a rational number. So we can say, suppose, I remember we talked about these connectives in the previous lecture, right? Suppose that So we wouldn't use given that or anything like that here, right? Because we are not given anything. We are supposing now, right? We are supposing that x is rational. If x is rational, then what is the form of x? Then x is equal to p upon q. For some integers, p and q, right? P and q are integers, right? And obviously q is not equal to 0. So this is the form of x here. So if this is the form of x, right, and we use the words then, suppose then. So after then, if x is rational, then we could say no. So another connective, x squared is equal to p squared upon q squared, right? So this is what we have so far. So now we can write, so because of this statement here, right, then we could use another connective by inferring from here. So we could say from here, we could use it with since, right? Since x squared is the quotient of integers, then squared is rational. So what do we want to show? We wanted to show that x squared is rational. So we started why x is rational. We proved x squared is rational. That's what we have shown here. So there is nothing left to prove because this is the contrapositive of the statement here. So we could say this is what was asked to be proved. Hence, our proof is complete. Right? Some people like to write QED. Some people like to put the box. Whichever one is fine. Right? So this is how we would prove something like this, where it's not easy to just start by saying let x squared be rational, or suppose that, or if x squared is rational, or suppose that x squared is irrational, and then start to prove, right? So this is one method that we can use to prove this. Of course, there are many other ways that we could tackle this, right? What's another way? Right, just to outline another way. We could think about okay, so because x squared is irrational here in the original question and x is irrational, we can use division into cases, right, which we'll get to at some point in time. So if the hypothesis, so this is just an outline of what else we can do. If the hypothesis is x is a real number, then we can divide this into subcases by saying x is a non-negative real number. You can also say that x is a real. No, not a real. Because x is a negative. So this, we had non-negative here, we have negative here. Negative real number. And then we can suppose that P implies Q. And then we can divide into cases. And then we can prove for each one. But this is a very, what we call an exhaustive. Exhaustive proof, right? It's a valid proof. It just will take a little bit longer. And this is much easier for me to understand because I already know the form of this. Okay, so this brings us to the end of 4.2. In the other lectures to come, we will continue from 4.3.